How does generative AI really work?
Have you ever wondered what's going on in the hardware when you're using ChatGPT or Midjourney? Well, in this video, we're going to dive deep into the mechanics behind generative AI. To explain, let's imagine we're going to a fast food restaurant together. Right, grab your coat.
Now, imagine each part of this restaurant represents a component in the AI processing chain.
Step 1. Placing an order.
Welcome to the Deep Learning Diner.
When you type a question or a prompt into an AI interface, envision it as walking up to a fast food counter and placing an order.
One bite-sized burger, please.
The counter attendant is the first point of contact at the restaurant. In our AI world, is the CPU, or the central processing unit. For the sake of this explanation, let's consider it to be an Intel Xeon processor, with its software responsible for overseeing the entire operation and ensuring that resources are allocated efficiently. In technical terms, the CPU decodes the incoming query to understand what kind of computational tasks will be required, then schedules these tasks, determining which should be handled by the CPU itself and which should be offloaded to the GPUs for more specialized processing. This is similar to sending out food orders to different line cooks responsible for filling different parts of the order. So perhaps you had one cook who is focusing on hamburgers, one who is focusing on French fries, and another who is focusing on a delicious dish of chocolate cake. In summary, the CPU's role is multifaceted. It decodes the query, schedules tasks, and fetches initial data, setting the stage for more specialized work that will be carried out by the GPUs. Step 2. The food processing team takes over. The next critical players in this factory are the GPUs, or graphics processing units. The line cooks of the restaurants, if you will. For this discussion, we'll focus on NVIDIA's NVIDIA A100 as a prime example. GPUs are specialized hardware designed for handling complex mathematical computations, much faster than a general-purpose CPU. They excel at specific types of calculations, particularly vector and matrix operations, which are foundational to machine learning algorithms. They are the expert burger makers, or they are the Lord himself who knows the secret sauce recipe with all 37 herbs and spices. In our restaurant analogy, think of these GPUs as specialized food prep stations, where your order is broken down into smaller, manageable tasks. Each GPU can handle multiple tasks simultaneously, thanks to its architecture designed for parallel processing. The NVIDIA A100 Tensor Core GPU comes equipped with tensor cores, specialized circuits that accelerate machine learning tasks. These cores are particularly efficient at performing the tensor operations that are ubiquitous in deep learning algorithms for tasks that require massive parallel processing. A100 GPUs are also used for training deep neural networks, for example, image recognition or natural language processing, or even scientific simulations. In summary, GPUs like NVIDIA A100 and NVIDIA's GeForce RTX series are workhorses in the AI factory. They handle the heavy computational lifting, from basic vector and matrix operations to specialized tasks accelerated by tensor cores.
Fire up the tensor grills. Time to do some matrix operations. I tell you, boy, here we don't just cook, we compute.
Step 3. Location, location, location. High bandwidth memory, or HBM for short, is a critical component in the AI computational process. often manufactured by companies like Micron. Unlike traditional memory types, HBM is stacked vertically, allowing for a more compact footprint and shorter data paths.
In this kitchen, we got more layers than a lasagna.
This design contributes to its high-speed data transfer rates. Think of HBMs as the advanced storage units that are strategically located close to the sorting stations. This proximity allows for quick and efficient access to the raw materials, data, and machine instructions needed for processing your query. In the context of our restaurant analogy, think of HBM as the food storage units, such as refrigerators and freezers, which are strategically located close to the food prep station.
In our storage units, we layer everything one by one, so they're easy to grab. So if you need some broccoli, you got it at hand. If you need a frying pan, here it is. Oh boy.
What sets HBM apart is its efficiency. And today, the most efficient HBM available is Micron's HBM3E. In our restaurant example, when the restaurant's order processing software is working well, all food stations should receive the orders and any updates in almost real time. Higher bandwidth would result in cooks getting food from the storage stations more quickly, and the more efficient layout in the restaurant resulting in more people being able to fit into the space and prepare a greater amount of food overall. Additionally, HBM is crucial for increasing throughput, the number of tasks or operations completed within a given time. In AI tasks, where massive data sets are often processed, high throughput is essential for efficiency. Step 4. Parallel processing. Burgers and fries, not burgers then fries. GPUs are designed for parallel processing. This means multiple GPUs can work simultaneously, each tackling a different part of the computational task. This parallel architecture is the cornerstone of efficient AI processing. In this case, the cooks in the fast food restaurant's kitchen can make hamburgers and French fries simultaneously, while another cook is waiting for your drink to be dispensed from the soda fountain. So we can imagine one cook on the fries, one cook on the hamburger, one cook serving up you a plate of ice cream, and another at the drink dispenser. And what this results in is super fast processing and super fast food. Step 5 is quality control and checking the order. Before finalizing the output, the AI model evaluates the generated text for coherence and relevance. This is an internal quality control mechanism. Once approved, the response is prepared for delivery.
Before we serve, we check every bite is cooked to perfection. Ooh, data delicious.
Step 6, the final product. The CPU, our Intel Xeon, resumes control. It coordinates the dispatch of the finalized output, ensuring it's sent back through the interface where the query originated.
Oh, well, I say, every single time this place does it. My delicious bit of data.
In summary, generative AI is a complex interplay of CPUs, GPUs, and high bandwidth memory, each with a specific role. Just think about it all the next time you go to a fast food restaurant. If this deep dive into burgers, fries, and AI mechanics was useful, feel free to subscribe, and I'll see you around for more AI videos.